Hello, everyone. Thank you for joining our session. Hope you had a good lunch and are having a good reInvent. So, do you know that 90% of the vehicles sold here in the United States have more than 5 ADAS features on them? Hence, ADAS has become a critical and strategic workload for our customers. I'm Venkat Devarajan, a solutions architect here at AWS, and I'm excited to be joined by Rivian, known for their adventurous EV vehicles. And today, we will dive into how Rivian accelerates their ADAS development on AWS. I'm Venkat Devarajan, a solutions architect here, joined by Madan Tota, Senior Manager of the Autonomy Group, and Narendra Challa, Lead Software Engineer. So here's a brief look at the agenda. I'll start off by sharing some of the trends and challenges that we see across our automotive customers, specifically with respect to ADAS feature development. And I'll invite Madan to the stage to dive into Rivian's ADAS story. He'll also give us a sneak peek into Polaris, their autonomy platform built on AWS. And then Narendra will share the AWS architecture details for data ingestion, simulation, and model training workloads. We'll also share some of the key learnings that we had along the way. So just a quick overview of ADAS, in case you're not familiar. So ADAS stands for Advanced Driver Assistance Systems. So these are the set of features that help with driver comfort and safety. Some examples include automatic emergency braking, lane change on command, and so on. SAE, or Society of Automotive Engineers, have 5 levels of driving automation, and ADAS falls under levels 2 to 2.5, and transitions to autonomous vehicles when we go to levels 4 and 5. So ADAS features are enabled in real time in the vehicle with driving models deployed in the car. So data from various sensors are fed into this perception model, and the output of this model, along with HD maps, is then used by the path planning module to activate the vehicle. So this is a simplification of an ADAS workflow, but it will give you an overview of how ADAS features are developed. So in the center, we have the storage and compute, and we have frameworks and solutions as a foundation. It all starts with data collection. Data is collected with specifically instrumented test fleet that OEMs have, and this data is ingested to AWS. Some data processing could happen at the edge, but we see a trend that most of the data processing is happening in the cloud. And S3 is a popular choice to store this data. Once this data is ingested, it's prepared and curated. So this is where we make sure that the data is valid and usable, and also extract the metadata so that we can search through this data set. Data is then labeled. So here is where we add bounding boxes, identifying objects, and so on. And then we augment this existing data set with additional data source like HD maps, speed limits, and so on. So now we have this data set that is ready for our autonomy team developers to build their model. So model and algorithm development takes place, and they go through a robust simulation and validation phase. And once they are satisfactory with the performance of the ADAS model, it is tested in a test fleet of vehicles. And once the model meets the KPIs in the test fleet, they are then finally deployed to the actual production fleet. So hopefully that gave you an overview of how ADAS workflow happens in AWS. And now moving on to some of the trends and challenges that we see across our customers. Data ingest and volume. This is a common theme that we see across multiple workloads, and it's even more pronounced for ADAS. So a ADAS level 2 system generates up to 400 gigabytes an hour, and a level 3 system generates upwards of 10 terabytes an hour. So we need efficient mechanisms to process and store this data. The next one is toolchain complexity. There are more than 300 tools today available for our customers to accelerate their ADAS development, and they often need to stitch together these multiple tools together. And then finally, time to market. ADAS feature development is a resource-intensive process and often has long development cycles due to its inherent complexity. And it also undergoes a robust verification and validation process since it involves human safety, and also there are certain regulatory standards that OEMs need to follow. So now we saw the trends and challenges. Now we're moving on to how AWS can help. Touching on the first challenge that we saw, which is data ingest. So previously, customers have two mechanisms to ingest data to AWS. They either drive the test vehicle back to the OEM location to ingest data, or they ship the hard drives. Both of them have its own challenges, where in the first approach, the vehicles often need to drive long distances to upload data, or the shipping the hard drives has logistical challenges, including maintaining backup drives. So in both the scenarios, the time between data collected and the data available to model developers is high. And to resolve this challenge, in just this reInvent, we announced the AWS Data Transfer Terminal. So this is a service that we actually collaborated with Rivian on. So you can think of these as physical locations present throughout the globe. So the test vehicle can simply go to a nearest location and upload the data. So you secure an appointment, go to this facility, and upload the data directly to an S3 bucket that you own. These locations are connected to the AWS backbone network as well. So Rivian's VP of Autonomy mentioned that using Data Transfer Terminal accelerated the data availability by 3 times when compared to the traditional methods. Moving on to the next challenge that we saw, which is the data volume. S3 has been a popular choice for building data lakes. However, we see a trend where customers move the data from S3 to a specialized file-based system in order to run workflows like simulation or model training. However, increasingly, we are seeing more customers directly using the data from S3 itself. A storage service needs to be carefully chosen based on your performance and cost requirements. However, S3 offers the following benefits. Inter-easy data access. So you might have compute clusters running in multiple availability zones for high resilience and availability. And S3 provides seamless access to the data that's present in the region. And intelligent tiering to optimize cost. As we saw earlier, data volume is exploding, especially with ADAS. And we need efficient mechanisms to store the data cost optimized. So intelligent tiering offers low-cost archive tiers, and based on the access patterns, it automatically moves data to low-cost tiers. Rivian actually uploads data directly to intelligent tiering, and Narendra will share how much they actually saved in his slide. And an S3 partition supports up to 5,500 get transactions and 3,500 put transactions. There are no quotas on the number of partitions that you can have on a bucket. So you can introduce entropy in the key naming scheme and even have higher partitions for your S3 bucket to support even higher get and put TPS. Your application might require a file system-based access interface, or you might need to refactor your applications to use S3 APIs. And to resolve this challenge, we also have S3 Mount Point. S3 Mount Point is an open source file-based client that translates S3 file system calls to S3 API calls. As you can see in the diagram here, so we have the storage at the bottom and compute in the middle. And Mount Point can seamlessly access multiple compute environments. So if you're using EC2, or if you're using ECS, Elastic Container Service, or EKS in Elastic Kubernetes Service, Mount Point could work with all of them. Mount Point supports data caching. So in most cases, we see that multiple epochs access the same data from S3. So with object caching, you're able to get 2 times faster reads. And Mount Point is also built on CRT. CRT is common runtime, a set of libraries that are written in C that implements AWS API best practices. So in the case of S3, if you're downloading a large object, it performs multiple byte range fetches so that network is optimized. And if you need even higher throughput, Mount Point also works with S3 Express One Zone to achieve 6 times more throughput for random reads. Now moving on to the next challenge that we saw, which is the toolchain complexity. So AWS is investing in creating purpose-built tools to accelerate ADAS development, and we saw an example in Data Transfer Terminal earlier. I want to specifically dive into the 2 solutions that are listed here, the Autonomous Driving Data Framework, ADDF, and the Virtual Engineering Workbench. ADDF is an open source project that provides modular artifacts for common tasks with ADAS feature development. So these common tasks could be data ingestion, simulation, visualization, and so on. So you can use these modules out of the box, or also customize it per your requirements. Virtual Engineering Workbench, or VEW, it presents a user interface with a self-service portal with environments that are pre-configured. So these environments already have the toolset that is needed, properly installed, configured, and the licenses managed. So this provides consistency across your team of developers, and especially helps new developers to ramp up faster. And then moving on to the final challenge that we saw, that is accelerating time to market. So our CEO, Matt Garman, in his keynote mentioned that we are the first to bring Intel, NVIDIA, and AMD chips. And we also offer our own custom accelerators with Trainium and Inferentia. GPU is a fast-moving space, much like the large language model space itself. So having access to latest GPU instances is critical. And we also have capacity blocks, so that if you want to run a short-term experiment, you can simply secure GPU capacity using capacity blocks. And we also made a bunch of improvements to capacity blocks that were announced just this re:Invent, including instance top and instance term. We also partnered with Qualcomm and announced DL2Q EC2 instance, which helps running AI inference in the cloud. And then running large-scale simulations with the AWS Batch. This is also a common trend that we see across customers, where they use AWS Batch to scale to hundreds of thousands of instances. AWS Batch previously supported only one container. So when you have multiple containers, for example, for your simulation software, or for your test cases, or for your sensors, you often need to combine them into one monolithic container, adding operational overhead. Now, Batch supports multiple containers per job. So you can seamlessly use Batch as is based on your environment. And then finally, synthetic scene generation and search. So this is still experimental in nature and is a research topic for us, but we are hoping that the technology would catch up in the coming quarters. So we are seeing potential where generative AI could be used to create scenes that are rare to occur in real life. We could also use generative AI to augment an existing scene and include new objects. And with that, I'll pass it over to Madan to dive into Rivian's ADAS story.
Oh boy, that was a good commercial, right? Every time I see the vehicles, I feel very happy about it. The colors and the designs, like, hope you guys all like the Rivians too. I'm Madan Tota. I'm a senior manager at Rivian Autonomy team. Before we start, I would like to ask you guys a simple question. How many of you agree ADAS is critical for driver safety and comfort? I see quite good full of hands raised, right? But everyone, think about this, right? Features like lane departure warnings, collision detections, avoided so many accidents and saved so many lives. So ADAS has become so essential for every automobile. Over the last few years, there has been phenomenal growth in this area, especially related to ADAS, self-driving, and autonomy. It became so essential for every automotive company to have necessary infrastructure and the tools required to do autonomy feature development. In the next 20 minutes, I will share about Rivian Autonomy Platform and the applications and workflows we built to accelerate our autonomy feature development. Our ADAS solution is called Rivian Autonomy Platform. It comes up with 13 plus autonomy features, 20 plus safety features. It has autonomy features like highway assist, lane change on command. It has safety features like collision detections, emergency braking, park assist, and many more. Our goal is whether you're driving or parking, there should be an always feature to improve the safety and improve the driving experience. In this example, you can see lane change on command feature. With just using the turn signals, you can guide the vehicle to do a lane change. When it is a safe time and when it is a right, it will do the lane change for you. In the next example, you can see a emergency braking when the collision is detected. We developed Rivian Autonomy Platform in-house to enable the optimal performance of our systems, and as well as the scalable for the future releases. These AI-enabled systems are performing very well, utilizing the vehicle's advanced compute and sensors on board. When it comes to the sensors on board, our Gen 2 vehicles has 11 cameras and 5 advanced radars. The 11 cameras captures 55 megapixels of real-time imaging with a top-notch resolution and dynamic range. Additionally, the multimodal sensing capabilities are enhanced by the radars, which has impressive 1,000 feet forward-facing detection range. Together, these technologies provide 360-degree sensing with overlapping sensor coverage, ensuring optimal performance in all conditions. Additionally, our data collection fleet mounted with the LiDARs. It has long-range and short-range LiDARs. They provide high-resolution 3D mapping, which is essential for our perception model training. With the combination of advanced onboard compute and sensors on all our fleets, we are collecting millions of miles to train our models. I would like to show you some sample data. So let's review some camera data here. This is a video wall collected from the data from our vehicles. On this video wall, you can see the examples of different scenarios, such as traffic lights, trucks, motorbikes, and as well as the vehicles, other vehicles in the road, the people walking on the street, parking lots, lots of highway driving, and as well as day and night scenarios. The diversity of the data is very crucial for autonomy model trainings. It ensures the system can perform in wide range of real-world scenarios. Let's review LiDAR data. Here is another sample of point cloud 3D data we collected with our LiDARs. It's a scene merged from multiple LiDARs. These provides high resolution, a detailed layered view of surroundings of the vehicle. This data allows us to identify obstacles, road surfaces, and as well as the objects with high accuracy. So this comprehensive approach allowed us to train a scalable and very reliable autonomy models. We have seen the different types of the data coming from our vehicles. Our fleet vehicles continuously upload this data to the cloud. We then store, process, augment this data, make it easy for the curation and labeling. The labeled data sets used for model training. The trained models and updated software is simulated and validated. Once the triage and engineering teams review the simulation outputs and as well as the dashboards generated from those outputs, if everything is good, we push the updated software to the vehicles. This cycle ensures us our vehicles are continuously learning and improving over the time. Looks very easy, right? I covered it in 30 seconds, but it's not that easy. So how quickly and how efficiently we do this is matters. Also, a lot of challenges to overcome. Petabytes of the data accumulated over the time, and it's increasing every day. The data complexity is very high. We're talking about the videos from multiple cameras and as well as the point cloud data and other telematics data. We need a better tools to visualize this data together. Many teams collaborate on this development lifecycle, starting from the data collection to the model deployments. Data silos may happen because individual teams works on the different stage of the life. We need more collaboration across the teams. And the solutions we choose, it should be cost optimized and it should be very scalable and it should be secured. And it should support automation to the extent possible. To overcome these challenges, we built a platform called Polaris. Polaris is Rivian Autonomy Data Platform. Polaris is a comprehensive solution designed to support autonomy feature development. To start with, it has a user interface layer, which we call it as autonomy data applications, which is a set of web applications and command line interfaces, and as well as the dashboards. These provide the engineers the ways to manage the data and utilize the data for autonomous system development. These are connected to microservices and data workflows. The services layer will have a lot of business logic, which is very custom to Rivian, and as well as the integrations with Rivian security services, and also communication between the all applications using the APIs. The data workflows like labeling, simulation, training will do the lot of data processing. All these are powered by AWS Cloud and AWS Partner Services. AWS services provide high-performance cloud infrastructure to handle the mass storage and high computational tasks. Together, and also we do use the AWS Partner Services like Databricks for our analytical engineering pipelines and MongoDB as our operational data store. Together, these components create a robust, scalable solution for autonomy data management as well as autonomy data operations. Let's review some of the few critical applications. Data discovery, or we can call log discovery, is very critical when you have petabytes of the data and your access patterns are random. When we think about the solution, we thought about the three things: what you can search, how efficient and accurate is your search is going to be, and once you find the results, what operations you can do. Discovery Search provides an interface for all the engineering teams to search any data related to the autonomy data lifecycle. It starts with the raw data, which are recordings collected from the vehicle, and then any derived artifacts from that data, like images, annotations. Search accuracy is powered by the metadata. We do process the metadata at various levels. It starts with the simple driver nodes, and then we extend that with the system metadata like which car uploading this data and which trigger generated that particular log. Maybe AEB trigger generated that particular log. And also which software version collected this data. There are different system attributes will be collected. Once the data lands in the cloud, the data quality check is very important. We want to make sure the data is up to the mark as expected so that we can avoid the bad data. So we label the data as DQ check failed if there is some certain camera is missing or a topic is missing or cameras are not calibrated correctly. This will allow us to filter the bad data on further downstream processing, which saves compute on the downstream pipelines. And also, it provides us statistics to understand what vehicles are sending us the good data and what is the problem with the data collection. We also process the data ingestion with the ML pipelines, which opens up the video content and identify the objects, generates the summary and attaches to the metadata, so that we will know manually drivers may not be able to take all the notes, but we can read from the scenes within the video how many cars are there, how many trucks are there, or anything else. Finally, the KPI analytical pipeline, they provide feedback back to the original logs. If there is any event identified within the KPI calculations, this particular metric tag will be attached to the metadata again. Different kind of combinations of the metadata improves the power search capabilities and as well as the efficiency of the search. Annotation teams, engineering teams, and triage teams, everybody from the autonomy teams will be able to find the relevant data very quickly and very efficiently. Once they find the data, they can visualize this particular log in this application, or they can create a batch of the recordings and send it for the labeling purposes, or group them as a data set and send it for training or simulations. Building an efficient search platform and integrating with all other autonomy data applications has improved productivity of our teams. And also it improved efficiency and all the ways to utilize the data. I think over the time, you will filter out all the bad data, and then data will be utilized more carefully. Once the data is curated, we need to do the labeling. We do a lot of manual labeling and as well as the auto labeling. Manually labeling a lot of the data is very time consuming and expensive. Auto labeling significantly speeds up this process. With auto labeling handling standard data sets, the human labelers can focus on fine-tuning challenging edge cases as well as the validations of the labels generated. Here is an example of our auto labeling pipeline output, which went through all the 6 cameras of that particular scene and identified the objects within those frames. We automated these runs to run every night, including the curation and the auto labeling pipeline, and as well as the dataset creation to make it ready for the training purposes. This is an example of automation what we did, and automation is the key for faster executions. Once we train the models, we need to validate the software changes, right? And also as well as the model updates. Doing this on real world vehicle testing at a large scale is very time consuming. Simulation provides a faster, safer, and efficient way to do the software validations. We built an application within the Polaris called SimDash, which allows the users to do scenario management, dataset management, and job management. An engineer can select a dataset and select a software version or a Git hash commit and submit the job to the backend services. The workflow manager, which is monitoring these SimDash applications, has some intelligence built in there. Based on the type of the job and priority coming in, it will check into whether it requires CPU compute or a GPU compute, or it can work with the smart instances or on-demand instances based on priority. It reconfigures the job config and submits to the AWS batch. AWS batch provides very high scale compute. It can actually extend to thousands of instances on our runs. We're running 90% of our simulations on Spot instances, which is very cost effective. And also we were able to simulate millions of the miles for every feature release. Overall, these simulation apps and workflows allowed us to validate the changes very quickly in a cost effective way. And as well as it improved our product quality by identifying the issues earlier in the stage, even before we deployed the software to the vehicle. Let's talk about the triage. Autonomous systems need to operate very reliably and safely. So quickly identifying and resolving the key issues is very critical. Here is a quick demo I'd like to show you. It's one of the component in our discovery applications, which is called Tag Explorer, which allows our triage teams and engineering teams to quickly go through the list of the events happened on the road. In this example, user is reviewing the driver nodes. The engineer identified a nodes called failed automatic lane change event. So they will click on that particular list item. It automatically streams the related event data to the browser into the visualization panel. So engineer can review within the 3D panel. Here is another example where engineer like to review the metrics tag generated by the KPI analytical pipelines. He is taking example of AV event. The engineer then can go through the list of the events happened related to the AV, and he is more interested to explore AV level 3 events. Then he click on that particular list item, and then it automatically streams the relevant data to the browser. So one of the key learning we have was pre-process the data as much as you can for the triage teams and engineering teams so that they don't need to spend too much time on finding the relevant data. It improves their productivity to identify the root causes of the data. The visualization tool is very critical. It allows us to debug complex system behaviors and review sensor data together. We ported open source application called Foxglow, and then we customized it to meet Rivian needs, especially to support the Rivian data formats and S265 video compressions. We built a custom extension framework to make it scalable and easy to build the new panels and as well as the new visualizations into this application. And also it supports web and desktop versions. When you don't have the internet coverage on the vehicle testing, the users can still use a desktop version of this tool. The tool is fully integrated into all our autonomy data applications so that wherever the engineer need to review the data, they can do a visualization. Either it can be a log discovery application or a simulation outputs page or a detailed dashboard page in the KPI dashboards. Just a one click on the event, we are actually streaming the data to the browser related to that particular event. Some examples here about this tool. You can see multiple panels here, the maps, video, and as well as the 3D panel. In this example, engineer like to review high beam assist data. He can review incoming traffic coming on the road, and as well as he can see how high beam is performing. So this is the way engineers look at the data. In this example, the lane line algorithm, we can review it. He can review the lane lines in a 3D panel and as well as on top of the video. So this is how engineers can debug the data once it reaches to the cloud. If there is a triage ticket or any incident or a KPI feedback loop identified an event, they can quickly navigate to that data and visualize using these applications. The autonomy platform we built with its applications and as well as the data workflows deployed in AWS Cloud has enabled us to achieve remarkable milestones in the last 1 year. The platform improved how we manage the data and how we process the data by providing the scalable solutions and as well as better data management and cost efficiency. A lot of collaborative features are supported by this data platform. The improved triage processes and insights from the KPI dashboards improved our product quality. With the scale and automation of labeling, training, and simulations, accelerated our time to market, our autonomy solutions. All right, given that, I would like to invite my colleague to do a deep dive on technology architecture behind this platform. Let's welcome Narendra.
Thank you, Madan. Hey, hello everyone. I'm Narendra. I am lead software engineer with the autonomy team at Rivian. So let's dive into details on how Polaris is built on AWS to process petabytes of data, train models, run thousands of hours of simulation to deliver autonomy features to our customers to power their adventures. Let's start with architecture. We collect the data from Rivian vehicles and upload it to Amazon S3 using Rivian or AWS upload stations. This data is stored on S3 and processed using event-driven architecture with SQS, batch, and Argo. The output of this stage is a dataset. These datasets are stored on S3 and are used for training. The training platform is built on Amazon EKS. We use Kuberai operator for running the training. When the training is run, it logs metrics and some artifacts to MLflow. The output of this stage is a model. We take the model and put it through simulation and validation loop along with the autonomy software. The platform is built on Amazon Batch and Databricks. Once we have good models and software, we deploy it to our fleet and eventually to our customers using over-the-air update. Now let's take a look at each of these processes a little bit more in detail, starting with data ingestion and processing. Data from customer fleet is collected by the Vehicle Cloud team at Rivian. This is stored on Amazon S3 with privileged access policies, encryption, and security monitoring in place. We process this data using AWS Batch to remove any personally identifiable information and also extract metadata and store it in our metadata DB. We use Mongo database for this. Next, we collect the data from Rivian vehicles or test fleet vehicles and upload it to Amazon S3 using AWS Transfer Terminal or Rivian Upload Station. Using event-driven architecture for put object events, we process this data using SQS and Argo. We run a bunch of workflows like data quality and indexing. Data quality ensures that the data is up to our standards, and indexing extracts metadata and puts it into the metadata DB. Now, metadata DB has all the metadata related to the raw data stored on S3, and this becomes the foundation layer for Polaris APIs and applications. One of the core applications is discovery. Users can search data using the metadata using discovery. They can directly visualize it using Polaris Viz, or they can create a data set for simulation or training using Cosmo. They can also create data sets or put it through our annotation or labeling process, which is our next big workflow. We do two types of labeling. One is manual labeling, and the next one is auto labeling. In manual labeling, we have human annotators that label the data for lane lines, bounding boxes for objects, and traffic signs. In auto labeling, we run batch inference nightly using EventBridge and Amazon Batch, where we scale to like tens of thousands of EC2 instances to run batch inference and store the results on S3 bucket. We further process this data into Parquet format using Ray. We also process this data to speed up the training process. The output of this Ray dataset cache generation process is the final dataset used for training. These datasets are stored on S3. Once we have the dataset, we put it through model training. This is the architecture. We start with EKS Terraform module and customized it to work with our stack and to deploy to different regions and different applications. It is able to interact with Amazon EC2 and S3 for compute and storage, and other services like CloudWatch and Prometheus for logs and metrics. We also use Grafana for visualization of these logs and metrics. Inside the EKS, a user can just enable a EFA plugin, and we will install the EFA plugin. Some of the interesting plugins that we have here are EFA and GPU. These translate Amazon EC2 resources like EFA network interfaces and GPUs as resources of Kubernetes. We have Fluentd and Prometheus add-ons, which collect logs and metrics and transfer them to CloudWatch and Prometheus. And we have storage plugins like EBS, EFS, and S3 Mount Point, which are used to access storage directly from the cluster. A level above, we have the job management layer. This is the core layer that is responsible for the orchestration. We use Queue, which has features like gang scheduling, preemption, fair share scheduling, and prioritization to schedule jobs or training jobs here, in this case, which use RayJob CRD. RayJob CRD is part of Kuberai Operator open source project. It manages PyTorch data parallel jobs on top of the cluster. At the top, we have the application layer or the job layer, where we run RayJobs or applications like MLflow or Polaris suite of applications. The user flows look like this. Users submit a job using Rivex CLI. Rivex CLI is in-house built tool that is built specifically to manage job training lifecycle. Users select different options like cluster name, region, image to use, and different resources and priority of a job, and submit the job. Queue schedules this job onto the cluster depending on the resource availability and priority. when the job is run, it logs metrics to MLflow and also some artifacts as well as checkpoints and images. Finally, we can also use Cosmo, which is a UI application similar to Rivex. It is meant for managing jobs directly from the UI. We collect different types of metrics when running the jobs or any applications for that matter. We collect application level metrics and operational metrics. Here, you see application level metrics that are collected by Prometheus and being displayed on Grafana. We have things like GPU, CPU, and memory utilization during the job, as well as some application-specific metrics like Ray object store memory. Users are able to debug their issues like slowdowns or out-of-memory issues using this dashboard. We'll take a look at the operational metrics later. Once we have a good model, we then put it through simulation and validation loop. Autonomy engineers use Polaris SimDash for this purpose. It is a UI application where users choose a data set and a Git or Docker tag, which translates to the software version to run the simulation. They can do on-demand simulation where we build the Docker image on GitLab CI during runtime, or they can choose Event Bridge to schedule a run where they choose branches that are static like main or a release branch along with golden dataset. Both of these flows use Amazon Batch. We were able to scale up to 200 times more in 2024 using Amazon Batch. Once Amazon Batch runs the simulation and evaluation, it stores the results on S3. These results are automatically analyzed by Databricks, and we calculate some KPIs out of these. Now, users are able to access these KPIs with the dashboards on Streamlit that are hosted on EKS. Users are also able to directly access the simulation results using Polaris Viz. This is very helpful for applications like triage. So these are the operational metrics that help with optimizing the environment as a whole. You can see different metrics like type of EC2 instances used, where we have most success rate. So we can optimize the compute environment to use those EC2 instances. We can also choose purchase options like spot or on-demand, and we can also choose best AZ. Finally, here are the key learnings that we have throughout our journey. Here are the key learnings for the compute. Cache your Docker images. When you have large Docker images, like NVIDIA Docker images that are 10 to 15 gigabytes, it can take a lot of time to pull the image every time. So caching these images in Army of the compute environment will save you tons and tons of time and as well as money. We were able to save up to $1,000 or even more for simulation runs. Monitor your GPUs. GPUs are probably the most expensive resources that are available these days, apart from storage, which is a snowball. You can monitor GPUs using NVIDIA GPU operator, or you can profile your applications to perform better using PyTorch or NVIDIA profilers. Using good scheduler. This is very critical if you want your workloads that are most important to finish faster. We use schedulers like Q as well as Amazon Batch to schedule our workloads for training and simulation. Using placement groups. If you have requirements for low latency between your applications, specifically like training applications, using placement group will reduce the internode latency. Also, this enables you to use EFA, which will enable high bandwidth communication between GPUs. Finally, if you want to scale very high on batch, having a larger job runtime will help scale it much higher. We were able to scale 2 to 3 times more by increasing the runtime from 2 minutes to 6 minutes. Here are key learnings from the storage. Enable request metrics on S3. These request metrics are not enabled by default, and enabling these metrics will help you identify issues like someone spamming your application and S3 is not performing well, like 5xx slowdowns. Using intelligent tiering, we were able to save 30% of our costs, storage costs, by using intelligent tiering. So intelligent tiering, if you don't know, helps automate transition of data between different tiers of storage depending on the access patterns. Using GP3 volumes, most of the systems on Amazon automatically default to GP2 volumes. GP3 volumes are newer volumes where you can get 20% price performance by using GP3 volumes, as well as you can control throughput and IOPS better. We have transfer acceleration. If you have applications that need streaming as well as visualization, you don't have to host some expensive file servers. You can directly use S3 with transfer acceleration enabled. So we were able to utilize transfer acceleration to full extent with Polaris Wiz. Finally, common runtime. So common runtime are some of the libraries that are written in C and C++ that will enable faster downloads and uploads. You can use Python Boto 3 with common runtime enabled, or you can directly use S3 mount point, which comes with common runtime. So what's next for Rivian on AWS? We are projected to grow 4 times in data storage, as well as 10 times our compute for training and simulation. So we can ship the features faster to our customers to enable their adventures. And we also have interesting projects lined up in 2025, like using generative AI for data curation and synthetic scene augmentation for training and simulation. We're also always looking to optimize our cost. So we are taking up many projects in 2025 to reduce inference costs for simulation and auto labeling, as well as have stricter lifecycle policies on S3 to reduce costs much further. Finally, we want to have a closed-loop data management system where we create data sets automatically depending on the model performance and take it through curation process, labeling, and trigger new training jobs. With that, thank you so much for attending. And here are our LinkedIn profiles. If you have any questions, we are able to take those questions now. And please rate our